We will talk a little bit about correlation functions and time correlation functions. Let us say you have two sets of data, the height of people in a classroom and their age. So normally the age will be correlated to the height, and you will have something like this. Now you can calculate the correlation between these two variables, height and age, using a single number, and we call this the correlation coefficient between two properties x and y, and this is equal to 1 divided by the number of measurements multiplied by the product of each individual measurement, and this is equal to the mean of the product of xi and yi. So this is the correlation coefficient between x and y. However, it is better if we normalize this so that this value fluctuates only between -1 and 1. In such a case, the correlation coefficient becomes normalized by where each summation is taken over all m measurements. Then if the correlation coefficient cxy is 0, it implies that there is no correlation between x and y. If it is equal to 1, then there is a positive correlation, a perfect positive correlation. And if it is equal to -1, then it means there is a perfect negative correlation. So if one quantity increases, the other decreases. If x and y are random variables which fluctuate around their mean, then the definition of the correlation coefficient changes a little bit and becomes summation over all measurements m multiplied by an individual measurement minus the mean of x. Here x bar and y bar are the average values of x and y, divided by the normalization factor, which ensures that this quantity fluctuates between -1 and 1. Good. This is also known as the Pearson correlation coefficient. Now in molecular dynamics, we usually have data at consecutive times, at specific times. So the way we use correlation functions is to find out how correlated is a certain data point at time t to another data point at a different time point. We call these correlation functions time correlation functions. The most popular of these is the velocity autocorrelation function. We will come to that. But a simple definition of a time correlation function, this is not normalized, is something like this. So this tells you how correlated is the observation x at time t is to the observation y at time 0. If x and y are different variables, then this becomes a cross correlation function. Now remember, now we are calling it a function instead of a coefficient because it varies with time. And if x and y are the same, then we call it an auto correlation function. The most popular of these, as I mentioned before, is the velocity autocorrelation function. In the normalized form, it is written as CVV as a function of time, and this is equal to 1 divided by the number of snapshots or the number of observations. Summation I equals 1 to n. The velocity of particle at any given time t. So this summation now is over all n particles. And since this is a vector, we have a dot product now divided by the normalization factor, which is essentially the initial velocities squared. So this is called the velocity autocorrelation function. It tells you how the velocities at any given time t are related to the initial velocities. If you plot this function versus time for a gas, it will typically look like this for the simulation of a gas. And this time can be very short. It can be a few nanoseconds or even shorter. The area under this curve is also called a correlation time or a relaxation time. And it tells you the time needed for the system to lose the memory of the initial state. This value of course is 1, here it is 0. So this tells you the time needed. Let me write that down. For the system, in this case a gas, it could be a Lennard-Jones fluid or an ideal gas, to lose memory of the initial state, or in this case the initial velocities. For a liquid, on the other hand, this curve looks slightly different. It becomes first negative and then equilibrates. And a question to you is, why do you think this is the case? We will think about it later in future lectures. Just like the velocity autocorrelation function, you can also have a rotational correlation function, and this has the rotational velocities, and this can be defined as c omega omega t, where omega is a rotational velocity and it is given by a similar expression. And normalized by the initial, sorry, there's a dot product here, rotational velocity. Now this quantity, if you take a Fourier transform of this quantity calculated in simulations, you can directly compare it to experimental data which comes out of infrared or Raman spectra, and in some cases NMR spectra. So this is a quantity that you can directly compare to what you can measure in experiments. So what do you learn from time correlation functions? First, we learn about system dynamics. So if the time correlation function decays to 0 very quickly, it means the system is highly dynamic and loses its initial memory. If it decays to 0 very slowly, it means it retains memory, its initial memory, so it's likely to be in a more crystalline state. You can also find out transport coefficients, and I will show you this in a future video. And you can relate this measurement directly to experiments. So this was a little bit about correlation functions and time